Okay, so let's start from the beginning. Welcome everyone to Math 1510, Theory of Deep Learning. Oh, no, Theory and Data Science. So we're just talking about the fact that there is a buzzing noise in the background, and that is due to the fact that there's 2 seasons in Toronto, winter and construction. And I got a suggestion that I should rent a cabin in the woods and ride out the pandemic there, which is a wonderful suggestion, except there is no Wi-Fi there. Right. Okay, so last time we spoke about different random matrices and the spectra that emerge in those random matrices. And let me remind you of the most important, what's PapaMask? I'm not sure. Of the most important example that we saw, which is called the Marchenko-Pasteur eigenvalue distribution. So imagine that you have a matrix whose entries are ID normal Zij. And imagine that these entries have a variance of 1 over n, and this matrix Z is of size P times n. Assume that this matrix is growing to infinity. It's a very large matrix, right? And the shape, as this matrix tends to an infinite shape, the shape tends to a limit which is called gamma. So it's just the ratio of the number of rows to the number of columns. So intuitively speaking, the columns in the matrix Z, the columns, there's n columns, p rows. The columns are usually referred to as the sample size, because you can think of each column as corresponding to a different sample from some data. And the rows are thought of as, let's say, I don't know, different features of something, okay? Now, given this infinite matrix, one can calculate its eigenvalues. And specifically, we're interested in the eigenvalues of the second moment matrix, which is ZZ transpose, okay? And what we discussed was that as the dimensions tend to infinity at a ratio gamma, the distribution of the eigenvalues tends to a limit which is described through the Marchenko-Pasteur equation. Someone wants to ask a question? No, I heard some noise. And here you can see the equation, and at the bottom you can see the shape of the distribution. Now, we also discussed how the shape of the distribution looks differently depending on the ratio gamma. And here you can see the distribution for various shapes. Now, notice that as gamma tends to 0, it means that P over n tends to 0, right? And that means that the sample size becomes significantly larger than the dimension, and therefore your distribution converges to basically a delta. So it's all of the eigenvalues are concentrated at 1. And that is to be expected because we know that Z is distributed as a normal with 0 mean and 1 over n variance. And if we have infinite, so to speak, columns in the matrix, you would expect the second moment matrix to converge to an identity. Do these words make any sense? Do they register as at least plausible statements? They do. So this is where things get a little bit more complicated. Now, notice that in reality, no one truly, so these type of distributions are very limited because they essentially model the distribution of the eigenvalues of noise, right? If you have Z, which is distributed as a normal, you can think of it as just being noise. No one likes noise. Noise is garbage. Garbage is meaningless, right? And so what would be the next step to study? The next step would be to study a noise plus some signal, right, case. So what does that mean? So imagine that we assume that Z is again normal 0, 1 over n, and that Z, the matrix, is multiplied by some positive semi-definite matrix sigma n to the power of half. Okay, so this matrix is basically rotating the noise in a certain manner. Now, assume that this sigma n satisfies the following very specific property. Sigma n is a diagonal matrix which has a fixed number of eigenvalues which are equal to, choose a number that you like, let's say 1, 2, and 3. And the rest of, oh, actually not 1, 2, 3. Let's do 4, 3, and 2. And the rest of the eigenvalues are all equal to 1, okay? So if that's sigma, what does it mean about x, which is equal to z times sigma n to the half? It means that you're just multiplying by this diagonal matrix. So it's essentially scaling some of the columns of z, right? Now, we're still assuming that p over n is tending to a limit gamma. But in addition, we're assuming that R is fixed, okay? R is fixed. And what we care about is the eigenvalue distribution of XX transpose, which is basically the second moment of this thing. So first of all, this model is called the spiked covariance model, and it was proposed by Ian Johnson in Stanford Stats Department in 2001, okay? Does anyone have any questions about this model? Any questions? So up to now, what you should understand is that it's basically Gaussian noise that is being multiplied by a certain matrix. And this matrix has all 1 entries on the diagonal, except a fixed number, which is not 1. So Neil asks, what is the meaning of the diagonal? Yes, so the answer to the second question Neil asks is, do you just keep adding ones to the end of the matrix? That is correct. So as n tends to infinity, all we have to do is just keep concatenating ones to the matrix, right? It's a diagonal matrix. Let's plot the diagonal matrix, which has here L1, L2, L3, let's say, and then 1, 1, 1, 1, 1, 1, 1. Da, da, da. Okay, so let's plot more. Okay. The first question of Neo was, what is the meaning of the diagonal? So the reason does anyone know why are we considering a diagonal matrix? Maybe I should ask it that way. Why do we restrict our attention to a diagonal sigma matrix? Why don't we consider general matrices?
Is it because you want to take the square root?
No, because you could consider general positive semi-definite matrices for which the square root is defined, right?
Is it because we're taking eigenvalues anyways? So if you like added an orthogonal transformation on there, it wouldn't make a difference?
Exactly, yes, yes, yes. So if you had a sigma, let's say, which is a non-diagonal matrix, you can always write it as something like, you can always do a U, let's say lambda U transpose, right? And then you can essentially absorb this U into the noise. And if you rotate random Gaussian noise by some orthogonal matrix, it's still random Gaussian noise, so nothing happens. Does this make sense? So this left U gets canceled, and the right U would get canceled because we care about XX transpose. Maybe I should write it here. It would make more sense. So basically, if you just plug the definition of X, you would get Z, oops, what is this? Z times U lambda U transpose, U lambda U transpose Z. So the U's cancel each other, right? And the ZU is just another Gaussian distributed noise, just rotated, but a rotated Gaussian noise is still Gaussian noise. I feel like I'm saying this in a horrible way. If you take a Gaussian noise distribution and you rotate it with an orthogonal matrix, it's still orthogonal Gaussian noise. What is the U that I've written? So imagine that instead of having sigma n, which is a diagonal, sigma n half, you would have, let's put here half. You would have something like sigma n equal to U lambda U transpose, right? So, and maybe I should also mention the theorem that we're kind of referencing without writing explicitly. If Z is a normal distribution with an identity covariance, if you rotate Z with an orthogonal matrix U on the right, let's say, then it's still normal zero identity. Nothing changes. That's the theorem that's justifying that. So that was the first question. So Neo, are you satisfied with the answer?
I'm still a little bit confused.
Mm-hmm. So your question was, what is the meaning of the diagonal, right? So the meaning of the diagonal is, it's a diagonal matrix which has a limited number of entries which are not equal to 1, and the rest are equal to 1, right? So when you say, what is the meaning of the diagonal, do you mean, why do we have a diagonal matrix and not a positive definite matrix? Or do you mean, why should we consider such a matrix in general? Or?
Oh yeah, I meant why would you want to tag a matrix on the noise? That's
because beautiful things happen if you do that, as we will see next.
Okay, I guess. Yeah, like, that's what I was.
Yeah, maybe it's not super clear at this point, but it hopefully will be very clear very, very soon. Is the sigma the actual covariance of the Z? No, sigma is not the covariance of the Z. It is not the covariance of the Z. Sigma is just a matrix that you choose. Do you just keep adding ones? We answer that. In what sense is this a model? I'm having trouble building intuition beyond just matrix processing. In what sense is this a model? So a model is a precise characterization of how data is generated. That's when I say model, that's what I mean. So this is explaining in a very precise manner how to generate some eigenvalues, right? And so you can think of this as a model that generates eigenvalues, and perhaps it satisfies some properties. Does this answer the question? I'm not sure how to. Maybe you could ask it a bit more.
Yeah, so sorry, can you hear me okay?
Yeah.
Yeah, I guess I just, earlier you said that this is a model, or I heard you say the word model when you were explaining this, and I just kind of, it's sort of unclear to me what
constitutes a model?
Yeah. I mean,
so a model is any equations that can be interpreted. A model to me is playing God. Like if you go outside and you look at data, right? Then data is just going to be some, something that you measure, right? It doesn't satisfy any equations. A model is when you write a set of equations that tell you how data is literally created. So Neo is saying Minecraft creation. I don't play in Minecraft, unfortunately. I'm sorry to disappoint. Maybe I should start playing Minecraft, but the words Minecraft creation mode do sound like what a model would be. So it's a precise description of data. which you can assume to be correct, and which you cannot assume on real data. Does this answer the question? No?
Is the target task to compute sigma such that we get whatever eigenvalues we want?
Oh, so the target would be to understand how does the distribution of the eigenvalues of XX transpose behave. I should have said that. Okay, so I think I've managed to answer to a certain satisfaction all the questions. Okay, so there's a series of papers that analyze this model and showed that the most beautiful phenomenons happen in it. So here's one example of a paper by Baik, Benarous, and Pechet. And let's just read their abstract to see what they're doing. So we compute the limiting distribution. So hopefully the word limiting distribution makes sense to you, of the largest eigenvalue of a complex, we don't like complex numbers, Gaussian sample covariance matrix when both the number of samples and the number of variables, so number of samples, in our notation would be n, number of variables would be p. In each sample become large. Become large means they tend to infinity when all but finitely many, say r eigenvalues of the covariance matrix are the same. The dependence of the limiting distribution of the largest eigenvalue of the sample covariance matrix on those distinguished R eigenvalues of the covariance matrix is completely characterized in terms of an infinite sequence of new Especially a phase transition phenomenon is observed. Okay, so what does this abstract say? It's basically saying that they're analyzing the distribution of the eigenvalues and showing that there is a special type of phenomenon that occurs for the top eigenvalues of the covariance of the matrix XX transpose. Here's another abstract. This is by Debusshy's Paul. I hope I pronounced it correctly. So it's called Asymptotics of Sample Eigenstructure for a Large Dimensional Spiked Covariance Model. This paper deals with a multivariate Gaussian observation model where the eigenvalues of the covariance matrix are all one, except for a finite number which are larger. Of interest is the asymptotic behavior of the eigenvalues of the sample covariance matrix when the sample size n and the dimension p of the observations both grow to infinity so that the ratio converges to a positive constant. When a population eigenvalue, this is a very critical sentence. Let's use green to respect it. When a population eigenvalue is above a certain threshold, the corresponding sample eigenvalue has a Gaussian limiting distribution. There is a phase transition of the sample eigenvectors in the same setting. So again, they're concerned with the behavior of the largest eigenvalue. So maybe this is not very clear. It will all become clear in the next slide. Here's a third paper on the topic by Baik and Silverstein. All of these people are extremely well known in RMT, by the way. So in this abstract, they say, we consider the spiked population model proposed by Johnston in which all the population eigenvalues except one, all the population eigenvalues are one except for a few fixed eigenvalue. All one except for a few fixed eigenvalue. The question is to determine how does the sample eigenvalue depend on the non-unit population ones when both sample size and population, so sample size is n, population size is p, become large. This paper completely determines the almost sure limits of the sample eigenvalues in a spiked model for a general class of samples. So it's not only Gaussian, they consider a much wider set of distributions. So based on these three abstracts, what you should get is that all of these papers look at the distribution of the eigenvalues of the spiked covariance model in the limit where n and p are large and tend to a ratio, and they observe a certain phase transition phenomenon. Okay, so let's see what is it that these papers prove. So this is an informal description of what they prove. So the first thing is that because we're looking at XX transpose, where we have something like Z sigma Z transpose, and sigma is a diagonal matrix with L1, L2, LR, and then a bunch of ones, right? So let me ask you a question. What would be the distribution of XX transpose if the number of these things, if R was equal to 0? What would be the distribution? If R were equal to 0. By the way, this number, this L1, L2, and so on are called spikes. And it will become clear soon why are they called spikes. Uniform.
It would just be the Marchenko-Pastur.
Marchenko-Pastur, right? Marchenko-Pastur, because again, if you have ZZ transpose where Z is normal 0, 1, then you would get the Marchenko-Pastur distribution. Make sense? So Karen, your answer is correct if N was infinitely larger than P. In that case, you would get all eigenvalues equal to 1. Does this make sense or doesn't make sense? It doesn't? Okay. Now, let me ask you another question. If you had to guess, what would be the behavior of the majority of the eigenvalues of XX transpose when R is greater than 0? How would they behave? If you had to guess, you know, most of the eigenvalues. If you had to make a wild guess. If you
Based on this on the slide, I'd say it's Marchenko-Pastur.
It is Marchenko-Pastur, but why is that the case? Because if you have XX transpose equal to Z sigma Z transpose, right? And sigma has a this is finite, right? Finite number of, you know, strange eigenvalues, and then a bunch of them are just some 1, 1, 1, 1, 1, 1, 1. Then the 1, 1, 1, 1, 1, 1, 1 would just create a Marchenko-Pastur, right? So it's a very reasonable hypothesis to make. Do you agree it's a very reasonable hypothesis to make? Maybe I should emphasize how reasonable it is by changing the ratio of this plot. So let's make these spikes very small, and let's make the ones significantly larger, right? So let's write a bunch of ones. 1, 1, 1, 1, 1, 1, 1. Do you see? 1, 1, 1. So basically, these things, which are there's many of them, create a Marchenko-Pastur distribution, right? Intuitively speaking, this is of course not a proof by any sort. And then the real question is, what is the impact of these first R eigenvalues? How do they impact the spectrum? And this is the beauty of the papers that we've mentioned. Do we assume N goes to infinity while R is fixed? That is correct. Yes, we do assume that. So the beauty of these papers is that they show that there's 2 cases you should consider. So let me try and make a plot. Here's a plot. So thus far, we know that most of the eigenvalues are going to be distributed as a Marchenko-Pastur distribution. So let me draw a Marchenko-Pastur distribution, right? This is Marchenko-Pastur for me. Now, the question is, what happens with this limited number of eigenvalues? The answer is, it depends on the magnitude of Li. If Li is large, very, very large, let's say, then you're going to get an eigenvalue here. So here on the x-axis, you have the eigenvalue. On the y-axis, you have the probability of an eigenvalue. Okay, probability, you can think of it as a count if you don't like probabilities. So if the eigenvalue Li is very large, then your empirical eigenvalue distribution of XX transpose is going to have here an eigenvalue. If on the other hand, Li is very small, let's say it's here, then there is not going to be an eigenvalue. So let me show you the equation. If, let's say, Lj is greater than some threshold, then your eigenvalue is going to be equal to this. If Lj is less than some threshold, it's going to be equal to this. What is this number? Does anyone recognize this number? I guess it's unlikely.
Is that the upper bound on the spectrum?
Yeah, exactly.
For the bulk?
Exactly. So it's this thing. This is basically lambda plus. So what it means is that if your lambda j is too small, then your eigenvalue is just going to be part of this Marchenko-Pasteur distribution. It's going to get sucked into it, right? If your eigenvalue is large, if lambda j is large, then your eigenvalue is going to separate from the bulk of the eigenvalues. So this is outlier, this is bulk. If lambda j is large, you're going to separate. Can anyone, first of all, let's see, does anyone have any questions before I continue the description? What is the intuition behind this? Why should there be a critical Lj? What is the intuition? What is the intuition? I think this is already intuitive because if you have infinite eigenvalues which are forming a shape of some sort, right? Then if your value is not large enough, you're just going to be part of the crowd, right? You're just going to be part of all the rest of the eigenvalues. The question is, are you an exceptional eigenvalue or are you not exceptional? If you are not an exceptional eigenvalue, you're going to be swallowed by the bulk of eigenvalues. If you're a truly exceptional eigenvalue, you would be able to separate, float away from all the rest. I have no intuition beyond this. What is the intuition behind large Lj not getting crushed as n tends to infinity? It does get crushed in some sense because the eigenvalue, the top eigenvalue is carrying a smaller and smaller density, right? Because the number of eigenvalues tends to infinity. So I think it does get crushed if we were to define crushed properly. If Lj is less than 1, if Lj is less than 1, you would converge to the lower bulk edge, if that makes sense. Because you can have like a gap here. What do the exceptional eigenvalues do? By the way, exceptional eigenvalues is just something I just invented, so maybe you shouldn't use this. If you tell to an RMT expert exceptional eigenvalues, they might not think of you kindly. So what do you mean by what do the exceptional eigenvalues do? What do they do? What? I don't know. I'm not sure how to answer the question. What do the exceptional eigenvalues do? So maybe you should use the word outlier. An outlier is an eigenvalue that is separating from the bulk because its LJ value was large enough to separate from the bulk. So there's other phenomena that are quite peculiar about this, which are also kind of interesting. No, you don't want to eliminate them. At the moment, we're just studying the distribution of the eigenvalues, Davis. At the moment, we're just studying them. You should keep in mind this idea of eliminating them in the future. It will come back to us. Your desire to eliminate them will come back in a future lecture. Can you give an idea briefly how they prove this? It's very complicated. I cannot provide briefly an idea how they prove this. No. I do suggest you go to the paper and look at the paper and convince yourself it is highly non-trivial. And I'm not aware of a simple proof for this either, but there might be. So notice that there's other interesting phenomena that happen here, which are highly non-trivial. For example, notice that the point at which an eigenvalue creates an outlier is quite peculiar. Does anyone notice, or can anyone tell me why is it peculiar? What is peculiar about the point of phase transition, it's called? So what is peculiar about this number 1 plus square root of gamma? Is there something peculiar about it? Let's start with no, actually, let's stick with this question. Can anyone identify something peculiar? Let me give you a, yes, it's less, well, Jack is on fire. It's less than the boundary of the bulk. That is correct. So basically, this value 1 plus square root of lambda is less than 1 plus square root of gamma squared, right? So this value is less than this value. So it means that, for example, if Lj is equal to something like here, Lj, then you might still be able to create an outlier. So the point of phase transition is not at the bulk edge, it's actually before the bulk edge. Do you agree this is highly strange? You do. It is strange because you can create an outlier while still being, while Lj is still inside the bulk. So that's one strange phenomenon. And the second strange phenomenon is that notice that even if you are above the phase transition, if you're above this threshold that's here, your eigenvalue in the spectrum is actually this quantity right here. Can anyone identify something strange about this quantity? Or something that's perhaps non-intuitive to a person on the street. If you tell this to a person on the street, why would they find this a bit strange? What is strange about this? So think about, what would you expect the value of the eigenvalue to be? Like, imagine you take a matrix which is of the type Z times a diagonal matrix times Z transpose, right? And sigma has this. I can hear someone wants to say something.
Is it strange because it's larger than Lj?
Exactly. Yes, it is strange because it is larger. So if you were to ask a random person on the street, right, I calculate an empirical eigenvalue distribution of these type of matrices, right? And under certain conditions, I get an outlier eigenvalue. and you ask that person, what would be the value of the outlier? What would that person say? They would say the value should be Lj, right? Because that's just corresponding to this eigenvalue. But in reality, you can see the value is Lj multiplied by 1 plus some small quantity. So the eigenvalue that you measure is actually greater than the eigenvalue that is creating the outlier. Make sense? Does anyone have any question? No question. Now, there's also phenomenons which are associated with the eigenvectors. If you found the outlier, you can solve for the eigenvalue, I guess. Yes, you can. Yes, you can. Yes, you can. So given the eigenvalues that you measure, for example, if you observe this outlier, you can do a small calculation and find the original eigenvalue that created that outlier. That is a correct observation. Now, in addition to analyzing the eigenvalues, you can also analyze the eigenvectors. Vectors. Some people have told me in my past that I pronounce the word vectors incorrectly. Do you feel like I'm pronouncing, like I put too much emphasis on, no? Do you think it's good? Okay, so you're good, okay. So someone just keeps making fun of me for pronouncing it incorrectly. So I'm like super self-conscious about my pronunciation of the word vector. So the phenomenon about the vectors is that the vectors, no, not on YouTube, no. I haven't reached the point of fame on YouTube that I get made fun of by people. I'm just at a point where no one's even making fun of me. Hopefully one day, you know. Hopefully one day. So the vectors satisfy the following property. Imagine if I ask you the following question. Take the eigenvector corresponding to the eigenvalue L1, let's say, right? And then imagine that you look at the top eigenvector of this matrix XX transpose. So you have one eigenvector, which is the eigenvector that corresponds to the top eigenvalue of sigma. And you have one eigenvector, which is a measured eigenvector. The difference between the two is one of them is an eigenvector, which is called like a population eigenvector, an eigenvector that's that can only happen if n is infinitely larger than p. And another eigenvector is an eigenvector that you measure empirically, like the top eigenvector. Imagine you calculate their inner product. What would you expect to get? What should be the relationship between the eigenvectors that generated the data and the eigenvectors that you measure in an experiment? You would expect them to be the same, right? You would expect them to be the same. The same way you would expect the eigenvalue, the empirical eigenvalues, to be the same as the population ones. But it turns out that they're not the same. So for example, if you're, I'm not really sure I see the distinction between the two types of vectors. So first of all, do you agree that if we have here an outlier eigenvalue, there is some eigenvector corresponding to it, right? So like for this outlier, you have some eigenvector. Do you agree? So this is what we call the empirical eigenvector. Now, in addition, you have the population eigenvector, which is basically the eigenvector of this sigma matrix that corresponds to the top eigenvalue. So it would be just basically E1 in this case. There's different ways to define the eigenvectors. One of them is that it's just the eigenvector that corresponds to, let's say, L1. Does that make sense or no? It's really just a basis vector. like in all cases. What do you mean by basis vector like in all cases? By the way, you can just use
Yeah, so
word.
sometimes I turn on my mic and it just blasts white noise.
Oh, okay.
But right, so you said, sorry, I forget the name of the
Empirical
eigenvector.
Empirical
The other one?
eigenvector, population eigenvector.
Right, so the population eigenvector won't, it's always an eigenvector of sigma, right? And so
Yeah.
won't that always just be an EI for some I?
Yes. It will
Okay,
be
all right.
EI. That's a very good comment. Thank you. Yes. Neo asked, isn't the empirical eigenvector like infinitely long? Everything here is kind of infinitely long, which makes this analysis. I'm not showing here like, proper definitions and proper math because I don't want to lose everyone within 5 minutes of description. And there is no time, everything grows. So hopefully now we understand that there is a population eigenvector and there is an empirical eigenvector. And the interesting phenomenon is that if Lj, which is this eigenvalue here, if it's below the phase transition, we know that the empirical eigenvalue is just going to be at the edge of the bulk, right? Moreover, we know that the corresponding eigenvector is just going to be correlated, completely uncorrelated with the population eigenvector. So that means that the eigenvector is just going to be some random vector in space. If your eigenvalue is too small to emerge. However, if your eigenvalue is above a certain point, then your population eigenvector and your empirical eigenvector are correlated. And this correlation increases. So for example, if this outlier was very, 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 very large, it would mean that Lj is very large. Therefore, this thing would be negligible, this thing would be negligible, and this whole thing would be just 1. So if your outlier is extremely large, it would mean that your population eigenvector and your empirical eigenvector are extremely correlated. Okay, so I think this is the most complicated result that we're going to discuss. This is as complicated as it gets. So let me skip this for now and show you a plot, a beautiful plot. So this beautiful plot shows you, here you can see the distribution of the, let's say, XX transpose or something similar. So here you can see a bulk, right? Here is the majority of the eigenvalues, and they form some continuous shape. And you can see that rho here, this is an outlier, right? And you can see they say largest eigenvalue rho is greater than B in blue when theta is greater than theta C. So there's some phase transition at which point your eigenvalue emerges from the bulk. Now, there's also this case in which your eigenvalue does not emerge. So this is the bulk and there's no outliers, right? Do you see? No outliers. So it's as if this eigenvalue got swallowed in the sea of eigenvalues. What a poetic description. Now, on the right, you can see how do the eigenvectors behave. Is theta the angle between the two eigenvectors? Theta is analogous to Lj here. Theta is just a population eigenvalue. if I remember correctly. But the definition of theta here is not very important. It's important to understand there is a phase transition. If you're above it, you emerge. If you're below it, you get swallowed in the sea. Now, on the right, you can see an illustration of the eigenvectors. So the U here, this is the population eigenvector. Okay. Now, here you have, again, the population eigenvector. Do you see how the population eigenvector is? Okay, this is the most crooked. Let me try to. This vector, this is the population eigenvector, right? And similarly here. Okay. Now, what you can see at the top plot is also U tilde. This is the empirical eigenvector, right? And here you can see also empirical eigenvector, empirical. Does anyone understand what is this plot trying to convey to you? What is it trying to say? Is it trying to say something to you? Does it have any meaning?
It's summarizing the results in the previous slide, right? About the angle between the empirical eigenvector and the population eigenvector.
Yeah. Yes. So the top plot is showing that the angle here, okay, I don't know the words in English. How do you call this type of an angle? I'm sorry, I don't know. I was taught geometry in Hebrew. Acute? Okay, acute. Tangent? No, not tangent. Acute. I have a feeling it's acute. Less than 90, yes, thank you. So this thing is less than 90 degrees. What does it mean for two vectors to be less than 90 degrees? It means that they're correlated to a certain extent, right? Correlated. And at the bottom, you can see that, oh, by the way, what does this cone even mean? This cone means that U tilde can be anywhere around this cone, and there is no way for you to know where it is. You can think of it as being equally probable to be anywhere on the cone. The only thing you know is the angle. At the bottom, you can see that U tilde and U are completely decorrelated in the sense that they're basically, U tilde is just equally probable everywhere. Now, notice that one way to write this in an equation would be to say that the empirical eigenvector, so this is the empirical eigenvector, is equal to the population eigenvector, this is the population eigenvector, multiplied by some cosine. The cosine is a measure of angle, plus there is some sine multiplied by noise. So this is an intuitive equation that's telling you that the population eigenvector is, it's basically a signal plus noise model. So here you can see noise, right? Here you can see the strength of the noise. Here you can see the signal, which is the population eigenvector. And here you can see how much is the population eigenvector being multiplied by, and this is the empirical eigenvector. Does this make sense? So why am I even showing you all of this, you might ask yourself? The reason is that I'm trying to illustrate how mathematicians have spent a lot of time and energy into developing very precise theorems that analyze spectra of different models. And these theoretical results tell you that if you take data and you compute a second moment matrix and you look at the spectrum and you see a set of outliers, then you know that these outliers are likely to be emerging from some set of eigenvalues which are larger than the rest. So it gives you some type of a theoretical model of some sort at the back of your mind that explains some empirical measurements. Okay, let us see. Now, thus far we've talking about eigenvalues, but there is also singular values that one can consider. So instead of looking at the eigenvalues lambda I of x transpose, one can look at the singular values of x. And this is this paper by Florent Benaya, Jorges, and Raj Nadakuditi. I'm probably butchering their names completely. So let's read what they say. In this paper, we consider the singular values and singular vectors of a finite low-rank perturbation of large rectangular random matrices. So basically what they say is they care about x equal to z plus m. Z is a random matrix that contains noise, and M is a low rank matrix. Let me verify. Yes, okay. I'm using different notations in the next slide, but let me just explain. So this is low rank, and this is a rectangular random matrix, okay? Now, what they say is we prove almost sure convergence of the extreme singular values and appropriate projections of the corresponding singular vectors of the perturbed matrix. So basically they do a similar analysis to what was done in the previous papers for the case of rectangular matrices. So let me show you precisely. So a low rank perturbation of a random matrix means that you have some Z, which is the random matrix, and you have a low rank perturbation, which here I denote by X, and you obtain Yn. Again, you have this asymptotic shape. And the only difference is that now we care about the singular value decomposition, okay? Now, I don't show here in these slides the results that they obtain, but you can imagine what kind of results they obtain. They obtain phase transitions on the top singular values, and they obtain some type of alignments on the singular vectors. So to summarize this part of the lecture, we've seen the circle law, the semicircle law, the Marchenko-Pastur, which are classical distributions that have been known for a long time. And we've talked about how if you have a finite number of eigenvalues which are not equal to 1, then you get the spiked covariance model. And in the spiked covariance model, you get interesting phase transitions. And there's certain generalizations where you have, for example, the singular values instead of the eigenvalues. And there's also other generalizations. Neo would like to ask a question.
I have a question. When you say phase transition, you mean the thing where after a certain threshold, you become an outlier? That's
yes.
what.
Yes.
Okay. Thank you.
Yes. 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 You don't have, by the way, to raise your hand. You can just interrupt me.
Okay. I was just wondering about that last question or last paper.
Mm-hmm.
Was the low rank part also random?
No, it's fixed. It's fixed.
Okay.
The low rank part is fixed in the same. The low rank part is analogous to the fixed number of LJs in the eigenvalue case.
Mm-hmm.
The thing is that this model is much more useful for what we're going to discuss in the next part of the lecture. So that's why I wanted to show this as well. Because usually in statistics, what you get is something like a mean plus noise, right? This is usually what you have in statistics, mean and a perturbation from a mean. And so usually what you care about in statistics is something like, mean plus noise, multiplied by mean plus noise, and you have an expectation on that. And so that's much closer to this type of model than to the previous model, right? Are there any other questions? No other questions. Okay, so with this, we're ready to proceed to the next lecture, which is called DeepNet Spectra, Layer-wise Study of Features. Layer-wise Study of Features. So a couple of lectures ago, we asked the following questions. We saw that different spectra in deep learning have a set of outliers and bulks. And we asked ourselves, what is causing these outliers? How many outliers are there? And what is the significance of the outliers, etc. And in this specific set of slides, I'm going to focus on the simplest quantity one can consider, which are the layer-wise features. Layer-wise features. So what are layer-wise features? Imagine that you have a data set which is balanced. So it consists of input images, cats and dogs, and labels. And we assume that I goes from 1 to n, where n is the number of examples per class. And C goes from 1 to capital C, where capital C is the number of classes. So I remind you that in one of the first lectures, we talked about pre-activations and post-activations. So if one has a fully connected layer, then the input to the fully connected layer is called pre-activations because they are, sorry, it's called post-activations because they're post-ReLU. And the output of a fully connected layer is called pre-activations because they're before a ReLU, right? Now, the notations I'm using is HIC because it's the ith example in the Cth class. H means that it's a post-activation, and L-1 means that it's layer L-1, right? Now, notice that one can take all of these HICs and define the following quantities. So we can define a set of class means for each one of the classes. So basically, you take, let's say, a multi-layer perceptron. This is a multi-layer perceptron where you have a bunch of layers, right? And then you feed images and you look here, let's say you have HIC of layer L. You collect all of those features and then you calculate a class mean for them. Does anyone, do you see that this is very relevant to one of the homeworks? I guess the current homework, right? Where you were calculating class means. Now, here's a definition. So the definition says that the class mean at layer L is just the average over all instances from that class. And the average is of the features at that layer. Now, in addition, we can define the global mean to be just the average of all the class means, right? Now, on the right, you have a picture that illustrates this. So you can see here, there is a global mean in the middle of the layer. And then there's two class means. Let's say this is the cat class mean, and this is the dog class mean. And you can see that the cat class mean has a cloud around it where you have 2 points. So this is cat 1 and this is cat 2. Okay. Now, similarly, you can define these covariance matrices that by now we've seen several times. So the first covariance is the between class covariance at layer L. So this is calculating essentially how large are the deviations of the class means from the global mean. It's basically checking how large is this shape, right? And we can define the within class covariance of that layer that measures how large are the perturbations of the features from the class means. Do you see how these quantities are quantities we've already talked about just in the context of the last layer? But now we're talking about different layers, right? And we can also define the second moment matrix, which is just a sum of three matrices. So you can prove that the second moment matrix is a sum of a rank 1 matrix of the global mean plus the between class covariance plus the within class covariance. So how does one prove such a claim? Is this clear to everyone, how to prove such claims? I'm not going to prove it, but can you imagine yourself proving such a claim? Possibly. Makes sense. Okay. Possibly. So let me show you how does the spectrum, emphasis on spectrum, so these are the eigenvalues of the second moment matrix looks like. So this is the second moment matrix. In this specific case, I'm looking at a multi-layer perceptron which has 8 layers and which was trained on the Fashion MNIST dataset. MNIST has failed us, we move to Fashion MNIST, right? And what can you see in this plot? So ignore the orange things, just look at the blue circles. You can see that there is a set of eigenvalues. These are the indices of the eigenvalues. This is the magnitude of the eigenvalues. You can see that there is a single eigenvalue which is large. There is 9 eigenvalues which are smaller. And then there is a bunch of eigenvalues which are very close to each other, right? And notice that this y-axis is on a log scale, which means that this gap is actually very large, much larger than what this plot shows. Is it clear what this plot shows to you? It is clear. Okay. So the question is, what is causing each one of these components in the spectrum? What is causing the top eigenvalue? What's causing the C-1 eigenvalues or 9 eigenvalues? And what's causing the rest? So here's a picture of how the spectrum looks like. This is a cartoon or a illustration, which is more, perhaps more clear. So we can see that there is one outlier eigenvalue, which is greater than the rest. Then there is a set of C-1 eigenvalues, which are greater than the rest. And then there's many eigenvalues, which constitute the bulk, right? Do you see how this picture is illustrating what's happening in the previous slide? So here it's in the form of a histogram, because here you have the eigenvalue and here you have the density, the probability, the counts. Whereas in the previous slide, here on the x-axis, you have the eigenvalue index, and on the y-axis, you have the eigenvalue. Previously, we mentioned that these type of plots are called scree plots, whereas these type of plots are called a histogram, unless you have infinite eigenvalues, in which case it has no name. Okay. Now, notice that in reality, you might have different variations of this cartoon. So you might, in some experiments, find something like this. In some experiments, you might see something like this. In some experiments, you might see something like this. So there's different variations of this cartoon that you might expect to find in practice. Now, in order to explain what causes this spectrum to emerge, I'm going to use something called a knockout. So a knockout is when you take a certain matrix and you try to somehow kill or eliminate a certain part of the spectrum. So imagine I take a certain spectrum that looks like this, right? And I try to eliminate the top outlier eigenvalue. How can I do that? So one way I can do it is by taking this matrix and subtracting some other matrix and seeing what is the effect. So if I take the matrix and I subtract, for example, another matrix, and I see that this outlier disappears, it means that the matrix I subtracted caused this outlier to appear. Another thing I could do is, instead of subtracting a matrix, I could project it away. So projecting away a matrix from the column and row space of another matrix. So let me just show you a very simple example that would make this super clear. So here's the spectrum. Here's a cartoon of the spectrum of the features, right? And you can see that there is a top outlier here. Imagine if I tried to knock out, this means knockout, a rank 1 matrix associated with the global mean. What would you expect to happen in the spectrum? What do you think would be here instead of this huge question mark? Centered. But what would be the effect of the spectrum? Squeezed. Squeezed in what sense? The bulk becomes smaller. No.
Oh, I guess you hope the same thing happens, but the largest outlier, the eigenvalue, goes away.
Yeah,
right?
exactly. That is correct. So notice that this is different than the bulk being smaller, right? This is different. So here's the picture of what we expect to happen. We expect that the largest outlier disappears, right? And one way to check that would be to just compare the eigenvalues of, so this is the eigenvalues of the second moment matrix versus the eigenvalues of the second moment matrix after we knock out this rank 1 matrix. And so eigenvalues which are on the diagonal are basically not being changed as a result of the knockout procedure, right? So if an eigenvalue appears on the diagonal, it means that knocking out the global mean did nothing to it. Whereas if an eigenvalue is above the diagonal, it means that the eigenvalue in the original matrix was large, and in the new matrix, it is smaller. Does this make sense? So you're essentially comparing the eigenvalues before and after the knockout procedure. So here's an example of real data. So this is the second layer out of 8 of a multi-layer perceptron, which was trained on MNIST. And what you can see is that the majority of the eigenvalues are on the diagonal line. So the majority of the eigenvalues are not being changed as a result of the knockout of the global mean, except a single outlier which is above this line. And the fact that it's above this line means that this eigenvalue was large before the knockout and much smaller after the knockout. So we can therefore attribute this outlier to the global mean. Does anyone have any questions about this? Is there intuition here? is there intuition here? So the intuition should come from our previous slides. The previous slides showed that if you look at the spectrum of a second moment matrix, where you have something like, if you look at the eigenvalues of Z plus M, let's say Z plus a global mean times Z plus a global mean, right? If you look at the eigenvalues of that matrix, then in a theoretical model, you expect to see a Marchenko-Pasteur distribution and an outlier which corresponds to that global mean. And the outlier only emerges if the norm of the global mean is large enough. So there is a certain phase transition. Above the phase transition, the global mean creates an outlier. So if you remember, there was a threshold, right, beyond which this vector would create an outlier. Does this answer in a satisfactory manner the question, Karen? Can't hear you.
Yeah, I'm just thinking. I might have to just do processing on this. So for now,
do you agree that the previous set of slides showed that in the context of random matrix theory, we know that a rank 1 matrix, right, a rank 1 perturbation can cause an outlier if the magnitude of that rank 1 perturbation is large enough. I mean, I guess the correspondence is not one-to-one, right? Because I showed something in the case of the spiked covariance model and not in the case of a signal like a mean plus noise model, but it's very, very close. So if the rank 1 perturbation has a large enough energy, then it's going to cause an outlier to emerge from a bulk, right? Do you agree with that? And so similarly, if you have global mean plus noise, then the global mean is going to create an outlier if the energy of the global mean is large enough. And what I'm showing here is an empirical verification of this fact. Because, theorems that hold for theoretical models in random matrix theory, there's no reason to believe they actually predict things in practice, right? So we want to verify. Why would the global, okay, so the global is sort of, the global mean is sort of a spike eigenvalue. That's correct, Jack, but I should say that the spiked covariance model assumed something like Z times sigma, which is some diagonal matrix times Z transpose, right? And so in our case, we are interested in this type of a model rather than these ones. So they are very closely related, but not the same. Is it just that if the global mean is small, then you don't need a feature to represent it? It's like lasso regression had a 0 intercept. No. I don't think so. No. Global mean is small, then you don't need a feature to represent it. Don't need a feature to represent it. Don't need a feature to represent it. I think that the way I'm thinking about it is you do feature engineering and then you try to understand what type of features you got. And so one thing you could ask yourself is, are the features that you got, do they have a strong global mean component to them? Like, are the features similar across the whole data set or not? If the global mean is significantly larger than the perturbations around the mean, it would mean that all the features in the data set are similar to each other. Does this make any sense, Alik, or it doesn't answer your question? Okay. Seems like my answers are not very satisfactory. Meditate on it. Okay. Does the largest eigenvalue always correspond to a global mean in terms of the second moment matrix? It does not. It does not. Because you might have a case where the global mean is very small compared to the class means, and then the class means would create an outlier. But in this specific case, you can see that the global mean is due, sorry, the outlier is due to the global mean. I'll show many more examples of this. So if this doesn't make sense, hopefully one of the future ones would make sense. So here's another example. Imagine that we look again at the second moment matrix, and this time we knock out both the global mean and the between class covariance. So this thing would be a rank C matrix. And we ask ourselves, what would happen to the spectrum of the matrix once we do that? Does anyone have any guesses? I guess it's pretty obvious at this point. So Neo is saying knockout basically helps you figure out where the eigenvalue comes from. That is precisely correct, Neo. Thank you. Thank you. So if we knock out, sorry,
I got a question further to that. Does that mean that like the global mean is an eigenvector for the largest eigenvalue, or it's just close to an eigenvector?
Close, yeah, close. I could create measurements that would calculate the alignment between the two, and those would show what you're talking about. Yes, yes.
Okay, thanks.
So Neo is correct. If we knock out the global mean and the between class covariance, then all the outliers would get knocked out. So this is what we would expect to see. Now, we could basically compare the eigenvalues before the knockout of the global mean and the between class covariance and after the global mean of the between class covariance. And what we would expect to see is most eigenvalues are on the diagonal, except a few which are above the diagonal. And those few eigenvalues would be attributable to the matrix that we knocked out, which is the matrix of the class means. So here's an experiment that demonstrates this. So here we can see on the y-axis the eigenvalues of the between class, of the second moment matrix, right? So this is the eigenvalues of the second moment matrix of layer 6 of a multi-layer perceptron trained on MNIST. On the x-axis, you can see the eigenvalues after I knock out the global mean and the between class covariance. And what we can observe is that a set of outliers are above the diagonal line. And so these eigenvalues are large in the original matrix and they become smaller after we knock out the global mean and the between class covariance. So therefore, these outliers can be attributed to the matrix that we knocked out and to the C class means. Neo asks, does that mean the outlier eigenvalues other than the global mean are close to eigenvalues of the between class covariance? That is precisely correct. Yes, Neo, that is precisely correct. And so let me show you a different view, which might be more intuitive to some. So do you recognize this plot that I've showed earlier? This is a plot of the spectrum of the second moment of the features in layer 7 out of 8 of a multi-layer perceptron trained on Fashion MNIST. And what you can observe now is a structure. There is one outlier, then there is 9 outliers, and then there is a bulk. at this point, we understand that the top outlier is attributable to the global mean of the features. The C-1 outliers are attributable to the between class covariance. And the rest of the eigenvalues are simply attributable to the within class covariance. Make sense? Now, what would be extremely interesting, at least to me, is to look at this spectrum for different layers of a network, right? So let us do that. So here you can see how does the spectrum look like for different layers. Oh, 1 second, let us not spoil ourselves. We observe the same for the spectrum of the Haitian, but don't understand the connection between these two. So Amireza is asking the most beautiful question, which is, how are these observations related to the Haitian? And this will be clarified in a future lecture. I will explain the exact connection between the two. Thank you for the question. So here, what you can see is the spectrum of the second moment of the features as function of depth. So this is layer 1. So this would be corresponding to the first ReLU, let's say. This is layer 2 all the way to layer 8. Can anyone identify interesting patterns here? Oh, I should mention, by the way, sorry to jump, but I should mention something. In blue here are the plot shows in blue the eigenvalues of the second moment matrix. And in orange, I'm showing you the eigenvalues of this matrix, which is basically the matrix of the between class covariance and the global mean, right? And notice that the eigenvalues of the between class covariance and the global mean are basically the eigenvalues of the class means, right? It's basically equivalent to, it's basically equivalent to plotting the eigenvalues of M transpose over C, where M is a matrix of the class means, right? And I'm plotting here in orange the eigenvalues of the class means. So does anyone notice what is the relation between the eigenvalues of the class means and the eigenvalues of the second moment matrix? So the eigenvalues of the second moment matrix are in blue. The eigenvalues of the class means are in orange. What can you see? What can you observe? So the orange converges to the eigenvalues in blue. They are the same in the picture. That is correct. That is correct. That is correct. And why do we expect that to happen? Because we know from the previous lecture that we expect the top outliers to be close to the eigenvalues of the low rank matrix that created them. This is where it gets complicated because I'm jumping from RMT to deep learning and backwards, but I see a nod at least from Karen. So
can I ask about that?
I've convinced one person, yes?
Yeah, so for the RMT stuff, the components of the matrix were these Gaussian variables.
Yeah.
That's not the case here, right?
Yeah.
So, but why should we expect it to be the same?
Right. So that's the thing, that the analysis in random matrix theory is making certain assumptions, right? And there's no reason to believe those assumptions happen in these experiments. That's why those theorems are, to me, suggestive of a phenomenon that one should investigate. I should also mention that, you know, I showed you like an epsilon from RMT. You can imagine the how much effort was put into generalizing those results, right? So one of those extensions, for example, showed that the results happen even for non-Gaussian data. You need some type of a bounded fourth moment condition that you see lots of time in statistics. That's enough for you to see these phenomenons happen. But there's other issues that are very fundamental and that basically make you wonder if any of these predictions would hold in practice.
Do you, even in the non-Gaussian case, do you still need independent coordinates?
Yeah, so independent coordinates is one thing. And there's also theorems that predict what happens in those cases. And there's lots of literature in RMT that extends those results, but it becomes a bit complicated. Definitely complicated for a discourse. But one could imagine using more advanced ideas in RMT to make certain predictions about deep nets. One could imagine. So Amirez is asking, you mentioned previously that the top outlier may correspond to a class mean, not necessarily to a global mean, right? I did mention that, Amireza, yes. But in this plot, you can see that this is not the case, right? You can see that the top outlier does correspond to the global mean. Do you agree? But hypothetically, what you're saying is correct, Amireza. If the global mean would be very small, let's say 0, there would be no outlier here. This would be gone. That's what would happen. Everything you've said, Amireza, is correct. I think what you expect to happen is what would happen. So let me move to the most interesting plot, which is this one. So again, here, what I'm showing you in blue is the second moment of the features for different layers. And in orange, I'm showing you the eigenvalues of the class means. So let's see, does anyone notice an interesting pattern that emerges? Greater gap between outliers and bulk, says Gina immediately. And that is correct. So you can see that at some point, initially, the class means are, so to speak, inside the bulk. And we see that there is no outliers. Do you see no outliers? As we go deeper into the network, eventually a set of outliers emerge from the bulk. And we can actually attribute these outliers to the class means, right? How do we do the attribution? By seeing that the eigenvalues of the second moment matrix in blue align with the eigenvalues of the class means in orange. And eventually, we can see that the class means are so separated from the bulk that there is a large gap. Amireza immediately says it can be interpreted as the SNR increases in deep layers, which is precisely correct. Karen asks, why might the bulk flatten to 0 as the depth increases? A beautiful question, Karen, to which I have no answer. No answer. But that's in some sense the essence of what deep nets are doing. They manage to kill the noise within a class and separate the class means information gradually. But also the C-1 outliers converge. Is that like in neural collapse? Wow, Gina is on fire, fire. Can anyone put the emoji of fire? I don't know how to put the emoji. So Gina already predicted the next question, which is, what is the significance of the class means being significantly larger than the bulk? Yes, thank you. Just put more than one if you can, just like a bunch of them. So the significance is that these class means are the class means that we talked about in the neural collapse lecture. And we can see how the class means, thank you very much, are significantly larger than the rest of the eigenvalues, which are the within class covariance, right? So this literally says that we have activation collapse. This gap is indicative of activation collapse. Can anyone tell me, how can we know based on this plot that the class means converge to a simplex ETF? So notice that when Gina says that she can see here neural collapse, that means that there's both activation collapse, right? Which means that the class means are significantly larger than the within class covariance, and also that the class means converge to a simplex ETF. But how can we check that the class means converge to a simplex ETF based on this plot? Riddle.
Do we also check, because I remember with the simplex ETF, we also looked at the angle between the two vectors and the length, that it's the same?
Yes, but in this plot, we have no access to the angles and the length, right? So we must resort to a different characterization of the simplex ETF. So what was the other way of defining a simplex ETF? Let me give you a hint. So what you can see here is that the ratio of the class means, the class means are basically having singular values, which, or eigenvalues, depends how you look at it, that becomes closer and closer to each other, right? Now, do you remember how one of the definitions of an simplex ETF, a simplex ETF is a matrix whose eigenvalue, so if let's say M is a simplex ETF, it means that lambda of M, why can't I draw? Lambda of M transpose, or M transpose M, is equal to 1 or 0, right? So you have C minus 1 eigenvalues which are equal to 1. Let me write a proper equation. So if we're talking about the ith eigenvalue, then if I is between 1 and C minus 1, the eigenvalue is, let's say, 1. Otherwise, it is 0. But you can have any number. It doesn't even matter if it's 1. It can be like 5 or anything you want. So one way to check if a matrix is a simplex ETF is to look if its eigenvalues are all equal to each other approximately. And you can see that all the eigenvalues are approximately equal to each other at the end. Now you can see that there is this extra thing. This extra thing is the global mean that we subtracted away from the class means in the neural collapse phenomenon. So by subtracting the global mean from the class means, maybe I can remind you what I'm talking about. So if you remember when we were looking, for example, at the angles, we did something like mu C minus mu G, mu C prime minus mu G inner product, right? Something like that. So by subtracting these global means, we essentially eliminated this outlier eigenvalue, if that makes sense. If it doesn't make sense, ignore the comment. The point is that the eigenvalues are equal to each other approximately, and that means that we have a simplex ETF. Does anyone? Is close enough eigenvalues a sufficient condition? Yes, it's sufficient, but you also need the null space, the rank 1 null space, to correspond to a once matrix. So it's almost a sufficient condition, almost. So to summarize, there's two phenomena. One is the emergence of the class means from the bulk, and the second one is the convergence of the class means to basically a simplex ETF. Okay, so what we've seen in these slides is that the features in a deep network have a two-pattern or a two-index pattern. So we've talked about features H, I, C, L, and the two-index structure is I and C. And because of this I and C structure, we were able to define a global mean, a set of class means, and deviations around the class means. And we show that the global mean causes the largest outlier, the class means cause the C minus 1 outliers, and deviations around the class means cause the bulk. Now, in general, Amireza is correct that this does not have to be the case because, for example, if the global mean was very small, then the global mean would not cause the largest outlier. And we saw that there is a relation to neural collapse in that the layer-wise within-class covariance collapses, which means that there is activation collapse. And we saw that the layer-wise features converge to a simplex ETF. With that, we are ready to move to the next part of our investigation. Actually, in the last lecture, I'm still confused. I think because we have no break, we're supposed to finish the lecture at 5:50 and not 6. And I feel like I keep stealing 10 minutes out of your life. Is that possible? I think that's possible. It is possible. So maybe we can spend the next 3 minutes on maybe questions. Does anyone have any questions? Because I don't think I can go over these slides in 3 minutes. I can try, but I don't think I'll be able to.
I've got a question.
You can ask.
Go ahead.
Oh, no, you can go first.
Okay. So on the previous slides, can you just pull open that plot, the discrete plot of the eigenvalues on the last page?
This one or this one?
Either one is good. So the distinction between sigma L capital T and then the other matrix, what's the difference of those two matrices?
So sigma TL is the second moment of the features. So it would be maybe I should define it explicitly. Sigma TL is the average of HIC transpose. And there's an L here. And the average is over I and C, right? And this means that this matrix contains all the information, the class mean information, the global information, the within class covariance information. Mu G transpose is self-explanatory. It's just a rank 1 matrix of the global mean. And the between class covariance is a covariance of the class means. Now, I should mention this probably would answer your question even better. If you...
There's an identity, right, with the 3 of them?
Yeah, this identity is very important. So this identity is analogous to the following identity that you hopefully know from probability courses that you've taken. So in probability, there is a definition which is called a variance. A variance of a random variable x is equal to the expectation of x squared minus expectation of x squared, right? Do you remember such thing?
Mm-hmm.
Now, if you rearrange the terms, you get that the expectation of x squared is equal to the expectation of x squared plus the variance over x. Notice that one way to interpret this is that expectation of x squared, if you're working in a multivariate setting, is just the second moment matrix, right? So it's basically this quantity, expectation of a scalar squared, is analogous to this quantity, which is the average of outer products. And the expectation of x squared is analogous to what? Is analogous to, let's use a different color. This is basically a mean squared. So we can think of it maybe as this thing. And the last thing is the variance. So you can think of the variance as maybe the within class covariance. Why do we have nothing corresponding to sigma b? Because in order to have something correspond to sigma b, you need to assume that your X is a Gaussian mixture model. You need to do like a different decomposition, if that makes sense. But you can probably think of a way to do the composition so that you would get a quantity that corresponds to sigma b as well. Does this make sense?
Yeah, I'm just like, so that plot, the fact that those eigenvalues are exact, are they exactly the same or
No, no,
just
no.
really,
So
really close?
I should have mentioned, if you look very, very closely, which we can using the power of technology that is available to us due to the global pandemic, notice how there is an ever so slight perturbation here. Do you see? Ever so slight perturbation. And this ever so slight perturbation is expected because of RMT effects. We know from RMT that the empirical eigenvalues, which are basically the blue eigenvalues, are going to be ever so slightly larger than the orange eigenvalues. And also, we know that the perturbation is going to be very small if your eigenvalues is larger, right? So here, small perturbation, because the underlying class mean eigenvalue is very large. Maybe I can show this. So you remember, if there's Marchenko-Pastur, if the eigenvalue, I guess it should be, okay. If the outlier is very far away from the bulk, then it's going to be very close to LJ. But if it's very close to the bulk, then it's going to be very far from LJ. Does this make sense?
Yeah. So, and what can you say about the eigenspaces of these two matrices? Are they like?
So you can measure the correlations between them. You can measure the correlation. Basically, I can write explicitly what that means. So imagine I take the second moment matrix L and I compute the top eigenvector. And let's denote it by V1, right? And then you can calculate the Frobenius inner product between this top eigenspace and the rank 1 matrix like this, right? Which is basically just equal to V1 inner product with mu G. I guess you don't even need the, like this, right? And so this would measure how aligned is the top outlier with the global mean. And I should mention also, if we're already on this topic, that basically in this case, none of these eigenvalues is going to be correlated with the class means. All of the eigenvalues, to like, if you look at the eigenvector of this eigenvalue, it's not going to be like mu c. You need to look at the whole space together, and that's going to be correlated with the whole space of the class means, if that makes sense. And that's related to phenomena that you know from linear algebra. In linear algebra, you know that if eigenvalues are distinct, then they have eigenspaces which are uncorrelated. But if you have a bunch of eigenvalues which are approximately equal, then there is no unique eigenvector. You have like a subspace, right?
It's crazy. It's yeah. I'm amazed.
Okay.
I have a question about the neural collapse part.
Yeah.
The neural collapse that we studied earlier was a neural collapse that's timed by epochs, right? But then now it's timed by layers. So it's not exactly the same.
Yeah. What a sharp observation, Neil. That is correct. So what I'm doing here is I'm just looking at what happens at supposed convergence. You know, what is convergence with crazy optimization algorithms like SGD? No one knows. But let's say epoch 350 is for me convergence. So I'm just looking at the spectrum at convergence.
Mm-hmm.
So maybe to address your question more precisely, HICL should also have a t. It's a function of time. And so what you care about is, you know, the limit as t tends to infinity and maybe as L tends to infinity, and that would probably give you neural collapse or something like this. I mean, L tends to infinity, I mean like the last layer.
Right. Cool. Would you expect that maybe neural collapse happen at every layer? So you don't have to you fix an L and it always just.
I'm actually, that's one of the things that I'm still on the fan zone? I'm still researching this. This whole thing is part of research, so I'm not sure. It's a good question. What do you think? Maybe you can help me with my research. Do you think it should happen in all layers, or do you think it should collapse in all layers or not?
I have a feeling that it will, just because all the layers are kind of same. It's like you just keep stacking things on top of each other. Like you just have to run more epochs. Like they don't create substantially different. Like I feel like if there has to be something, that if the layer has to one collapse and the other don't, then they have to serve a very distinctly different functions. But if they're all just activations, I guess maybe they all look the same. You see, like it's a matrix plus a ReLU plus
But notice that the first layer, it's almost clear that there is no way that neural collapse would happen in it, or it's very hard for me to imagine how it would happen, because in the first layer, imagine you have like one layer neural network. So you have something like X, which is your input data multiplied by a weight, and on that you apply sigma, right?
Mm-hmm.
So that's like one layer neural network, and you look at these features and you wonder, is there a neural collapse? So in fact, one of the lectures that I'm not sure if we'll get to analyzes what happens in this model when your weight matrix is of infinite size, and they show that neural collapse does not happen. So there's one example of neural collapse not happening in a single layer network. And the reason is that it's very hard for you to be able to collapse data using just one matrix and a ReLU. That's kind of my intuition, but it probably makes little sense. Try to do the following exercise. Imagine I give you a very simple distribution, which is a two-class Gaussian mixture model, something like this, right? Imagine that you use a ReLU and you're trying to collapse this data to the class means, let's say. Then it's not actually possible to do that, I think. Because your ReLU is kind of like scissors, right? It's kind of cutting somewhere, but it's impossible to cut in a single place a Gaussian and to make it collapse. This is a horrible explanation, but does it make sense?
Is there like a minimum number of cuts you have to make sure you always,
exactly.
I see.
Like what I'm imagining is, imagine you multiply this by if you take the data and multiply it by the label, and the label is like plus minus, you would get something like the two Gaussians are on top of each other. If you just, if this is 0, let's say, and the labels are plus minus, then if you multiply by the label, you get two overlapping Gaussians, and then you have a ReLU that you can cut with, right? Scissors. So let's say you cut, I don't know, here. If you cut here, then your data does not collapse because there's still variance. So where do you cut? Does it make sense?
Okay, I'll think about it. It's pretty cool. Yeah, maybe once you figure it out, you can let us know.
Yeah, let you know. Okay.
Yeah, I have one more question. So for the PyTorch, instead of using the matrix matmul, and then that thing transpose, I just use outer instead. Does that also work?
Yeah, I think it should work.
Okay, I just want to double check in case if I got it wrong. But the final outcome after running it looks like just collapsing. So I guess it's working.
Okay. Yeah, one thing about outer, I'm not sure if it works with a batch. Does it work with a batch?
Oh, I just iterated over the batch.
Okay, yeah.
So
that's the one thing that it's kind of unfortunate, because I'm worried that some students will solve all the questions in the homeworks with iterations. And it's, you know how in some languages it's bad practice to iterate because it's very slow. Like in MATLAB, if you iterate, you're doing things incorrectly. So it's fine for the homework, right? You can iterate as much as you want in the homework, but you should remember for future life, when you PyTorch outside of this class, that usually you shouldn't be iterating. You should use operations which work on the whole matrix, on the whole tensor.
I see. When you have like because a batch is a tensor, right? It's not a list of tensors. So yeah. I didn't know that you could.
Sorry, if you just iterate on things, then it's kind of like you're telling the GPU, make this calculation, make this calculation, make this calculation, right? And then it's going to be slow. But if you just throw at it a huge tensor, it would know how to parallelize it more efficiently.
I see. Okay, I will keep that in mind and think about it. Thank you very much. Maybe that's why it took so long to run, because
I think in general it takes long to run. It took long to run for me as well.
Okay, sounds good. All right, thank you very much. Have a good day.
You too. Is any server down for anyone else? Yes. Yeah, just switch to Fashion Amnesty. Fashion Amnesty is more stable.
I have a quick question.
Mm-hmm.
I was wondering when would be the last few sessions where we have the presentations? Do you know the dates?
Yeah, I need to calculate that, but I think we need something like 4 lectures. When I say 4 lectures, I mean 4 hours for students to be able to present. So if you take the last lecture minus 4, I think that's, so when is the last, actually I need to check this.
I wasn't sure about that.
So in the first lecture, I claimed that the last lecture is on April 9th. And I probably took that date from the internet somewhere. But it is possible that I'm incorrect because I don't actually, does anyone know when is the last lecture? Is it April 9th? I took it from some official calendar, but I have a tendency of confusing official calendars for undergrad and grad studies. In any case, I'll send an email, definitely.
Thank you.
So if it's April 9, it means that that's a Thursday. So that's one of the presentations. And then on Monday, which is April 5, we have more presentations. And April 1st, we have more. So it seems to me like April is when the presentations would take place.
I'm curious about the distribution of marks for the presentation. I'm just noticing just the asymmetry of like presentations are 5 + 1 minutes, and the report, like, it's clear to me how the report gets us 20%, but the 5 minutes for 20% seems a little scary.
It's very crucial 5 minutes of your life. Yeah, yes. I can redistribute the grade if that's concerning.
I have no objection. I'm just curious about what marks I should be, like what targets I should be aiming to hit in those 5 minutes, beyond just like summarizing what I did. And
I think somehow it should be somehow analogous to the report in that maybe spend a little bit of time on summarizing the paper, but don't go into like, insane details or something. And then the rest of the presentation focus on, what novel thing have you done? Try to make it approachable because, there's many people in the course who are probably less familiar with the topic that you chose on
I've got lots of like pictures and stuff. So I give the terse
picture is good.
definition, but like
Yeah, picture is good.
Cool. Thanks so much.
Professor, you just mentioned so you said we should do something on our own. So do you mean like can we like just find the paper and just run their code and to see how the results come up and how can we improve those results?
Yeah, so it's either it has to be either some theoretical result that you can prove in addition, or some novel observation, or some modification to their experiment that is interesting and leads to some insight, something new, something exciting.
Sure, definitely. Yeah. But